Both of us single dads from the Midwest, we can talk about it. Both of us single dads from the Midwest, we can talk about it. Both of us single dads from the Midwest, we can talk about it. Or we can get gully, I'll size up your body and put some white chalk around it.
Welcome to the Single Dads of the Midwest, episode 12. I'm joined by the notorious Nick to talk about things like space, the universe, and whatever we might think about. I do want to put a disclaimer on this podcast that neither Nick nor I are physicists or, expert level scientists by any means, so this will simply be an amateur discussion. So please take everything we say with a grain of salt and do not take us to be arbiters of scientific fact. That being said, I'm looking forward to this amazing discussion. Nick, why don't you introduce yourself?
Hello, listeners in the Midwest, apparently. That's news to me. I'm Nick. I write code for a living. And a friend of mine connected me with Alex here to share some ideas or just chat, really.
Awesome. And that friend is Don, aka Sheldon. Shout out to him for keeping this podcast alive and running. I also, while not formally writing code, work in programming to some extent, or I guess software in the Silicon Valley. So we might have some shared background there. So let's start with the question that you actually asked me before we started recording. Why don't you ask it to me again?
Okay, so this is a question I ask lots of people that I have some kind of relationship with. And it is, what shape do you think the universe is?
I don't know. So my first instinct is that it doesn't really have a shape. But I don't know if that's the scientifically correct answer. But I'm just going to go with it. I would say no, it doesn't have a shape that we could kind of quantify in the normal way we do. But maybe I'm wrong.
Okay, well, as far as I know, we don't know the answer, but there are some things that you might logically state about the shape. And maybe shape is also kind of the wrong word. More specifically, I would ask about the topology of the universe. But that word might scare you away initially.
And is there something, well, in terms of topology, I'm thinking of like geography of like bumps and different
That's topography.
Topography, okay.
Those are similar words, and they are related. I'm not sure how they're related, but they definitely are related. Topology is a branch of mathematics that's all about knots and surfaces and braids and stuff. So one way to think about it is the math of how things are connected. So maybe I can ask the question again. How do you think our universe is connected to itself?
I feel like that's such a broad, that's like asking what the meaning of life is. But I feel like obviously there's a relationship between space and time. I mean, we see that in like physics equations and, there's atoms that are like stardust is like the same atoms that we have. So there's like a connection to like everything in the universe in that sense. But I would have a hard time going probably deeper than that.
Okay, so maybe we should play with the toy universe first. So have you ever played the video game Asteroids?
I have not.
Okay, well, one of the defining features of the game, and this is true of a lot of video games, is that if you walk off the left wall, or the left side of the screen, you show up on the right side.
Yes.
And if you walk off the top of the screen, you show up on the bottom.
Okay.
So Asteroids exists in a 2D universe, and it has a topology that is strange. Because does the real world work that way? If you walk off the left side of the real world, do you pop back on the right side?
Well, theoretically, the universe is ever expanding. So is there ever like an endpoint where you could even like loop around, like from left to right in this instance?
Well, we don't know, but we don't know it's not like that. That's the thing. And there's some convincing reasons why you might think it does work that way, although a little more complicatedly than our 2D asteroids world.
And there's like a dimensional issue too, right? Because like we think of like XYZ, like this is like the only math in physics that I can go up, but we think of things in like an XYZ dimensions or 3 dimensions. But like in the universe, you're also like, you can don't you get to like 4 dimensions in a sense? Like when you incorporate, I guess, space and time.
Yeah. So we usually think of those four. Some models have more because the dimension is kind of like a free variable. So you might consider asking a question about a point in space at a specific time, but maybe if you're doing more advanced physics, you have other qualifiers you want to put on that point in space.
Got it. Yeah, this is tough. Like conceptualizing the universe. Like we talk about universes in a very commonplace sense, but like conceptualizing its limitations or our understanding is like really, really difficult. I mean, it's difficult even for actual physicists, but even much more so for the layperson.
So maybe if we jump back to the video game world,
Yeah, let's do that.
we can do a little thought experiment. Um, Imagine the screen as a piece of paper, and we just said that going off the left side brings you back to the right. So in your head, can you glue together those edges?
Yes.
And what shape does that give you?
A cylinder, basically, in a sense.
Yeah, so we can already see that, like, if we had a third dimension to bend this surface, this flat plane into, we could make the rules make sense because we can wrap the edges around into a cylinder.
That
and
makes
then
sense. Yeah.
there's no seam. Okay, so now can we do the same thing with the top and the bottom of the screen?
Ooh, that'd be hard because you'd have to like fold the cylinder at that point.
Well, so we already bent the thing. There's no reason we can't stretch too. Topology makes no difference between bending and stretching.
Okay, then
Or it
theoretically,
doesn't.
yeah.
It doesn't care that there's. It doesn't care if you bend or stretch the surface as long as it stays all together. You haven't torn it somewhere. So what would happen if we stretched everything and bent it and brought the top of our cylinder back around to the bottom?
Now you just have like this loop, basically, like this infinite loop.
Yes, and we call it a torus or a donut. Is like the usual everyday object that we think of, and
Yeah.
that's the shape of the asteroids universe. If you had a third dimension that you could like look down on asteroids from, that little spaceship exists on the surface of a torus. And when it goes up, it's actually going around the inside, and when it goes left, it's actually going around the equator.
Oh, that's an interesting way of like it's easy when you break it down like that. It's easier to conceptualize. That's very interesting.
So this is the question I was asking about our real world. But obviously, our real world has more than 2 dimensions.
So yeah, theoretically you can go beyond the donut. Though I think I have at some point heard of like the universe being kind of like this donut shaped thing, although I never heard the term torus.
So our universe probably wouldn't be a donut per se because it doesn't have an explicit left or right edge that we know about. So we might need a shape that's a little more hard to understand. But it could have this property of not really having edges per se. So the consequence of that would be like if you went in a straight line for far enough, you might end up back where you started.
Well, assuming that there was some sort of assuming it wasn't ever expanding, yeah. Or like there was or well like if it never ended, then it would never be able to loop around theoretically, right?
So that's another possibility. It could be that our universe has an infinite amount of space. That there's no boundary. You could just continue in any direction. Like a flat, when you draw a graph in math class, and there's an infinity that you can never reach. But there's both of these have a thing in common that I like to think about, which is what would an edge be like? Let's assume that our universe is a closed box.
Okay.
what could the edge possibly be like?
Oof. I'm thinking Interstellar, but I don't think that's probably what it is in real life.
I've never
um,
seen that movie actually.
oh, I feel like given that your passion for this subject, you should definitely watch Interstellar. It does have some interesting elements, definitely not fully scientifically accurate, but I do feel like this would be in the space genre in terms of movies.
All I know is that someone claims the fifth dimension is love, and that Anne Hathaway's in. And that pretty much sums up my
This is
knowledge.
true, but I would still watch it. I think it's at least worth watching, even if I don't think it's the greatest movie. I still think it's a good movie.
Okay, I'll propose that for my next online movie night, thanks to COVID-19.
Okay, I do recommend. But yeah, going back to if there was an edge, what would the edge look like? I feel like that's so hard because like you have to go like you said beyond the donut. It's more dimensions than that, and then at that point, it's like hard to think of something that we could like metaphorize in like a real world setting. Like we use the metaphor of the donut, but it's hard to think of what would be like the next metaphor in terms of
Well,
conceptualizing it.
I'm actually proposing that like let's assume we all live inside a box, and there
Okay.
actually is an edge somewhere, and you could walk up to it, and you would say, "Damn, that's the edge of my universe," and there's nothing outside of it. But what would it be like? What happens if you poke it? If you throw a ball or you shine a light at this thing, what happens? How do you know it's there?
Ooh, it's a good question. I mean, if you're in a box, there would be some, but like, is there another universe outside of the universe, or are we just
Well
conceptualizing the
then,
idea of one universe?
if there's somewhere else to go, then it's not really a universe, is it? You've
Sure.
just built a wall.
Uh, I guess yeah. I mean, I guess nothingness comes to mind, but I don't know how you would conceptualize nothingness.
Uh, so one thought experiment I try is if you threw a ball, you uh, and let's say it bounces back. Does that sound like a reasonable rule?
Sure, let's start with that.
Well, it turns out that would violate conservation of momentum because your ball was going one direction, and then your ball changed direction, and the edge of the universe probably didn't absorb and send back momentum because that would be very strange. So it would be like a problem if you could have this perfect reflective surface.
Yeah.
That would be weird.
So would it just like stop dead in its tracks?
But that would also be bad because the ball was going forward and now nothing is moving forward, which has a similar problem.
Is there a way out of this paradox?
I'm not a physicist, but I don't think so. This is why I personally believe that there is a curve, that there's a wrapping around, because
Hmm,
that way you don't need an edge.
occur. But you would still hit like a finite endpoint though at some point, theoretically.
Um, okay, well we can use an
Well,
analogy.
multiple endpoints. Like if it's curved, it's going to be obviously different locations. But yeah.
Ah, that's we can dig into that. So um, I know 7 or 8 billion people who live in a 2D world, and they can go as far as they want in one direction and end up back where they came from
Okay.
because they're all us because we live on Earth.
Yes, I figured that was the metaphor.
Right.
Wait, but
But
isn't it a 3D world?
well, it's a little different. This is an analogy, but it's the same basic idea. Uh, Up close, the ground looks perfectly flat. But we all know, except for the flat earthers, that um, there's a curve to the whole world, and
Yes.
on large enough scales, the curve wraps back around on itself.
Okay. So you're kind of conceptualizing space in like the next dimension where it's like this similar idea of like it being a curve, but then we like experience it in one level less, kind of like day to day. if that makes any sense, or one
Um,
dimensionless.
well, it's a little like that, but also, it turns out with a weird geometry like this, if you only look at a small region, it's impossible to tell that something is weird.
That makes sense.
And so the our universe is obviously enormous, and we have a hard enough time telling the Earth isn't flat without like tools. So if you're talking about a sphere like billions of billions of billions of times larger than the Earth, how could we possibly notice that there's this little bit of curve that adds up?
True. I guess the only way is that at some point you'd have to get enough technological advancement to create like a measurement in the same way they did with like the chains on like library on like Egypt or like there was like that chains experiment in ancient civilizations where they measure the curvature. Something equivalent of that where there's a technological advancement where you're able to do something of that sort.
Yeah, you need to invent something to try and measure this hypothetical bending. We're not, and we actually have an experiment that does that. One consequence of this idea of a curved universe would be that you would see copies of stuff, or you might see copies of stuff. So you've probably been in like an elevator or something where there's two mirrors facing each other,
Yep.
and it looks like it goes on forever, right?
Yep.
Well, a similar thing would happen in a closed, curved space like this. You would look forward and you'd see an object, and then you'd keep looking forward, and the same object would show up again, but it would appear to be, one rotation further away.
Interesting.
You'd see copies on copies until eventually your eyes couldn't tell the difference anymore, or the sphere is enormous. One of the two.
Wow. That makes sense. I mean I never thought about it like that, but with the elevator or there's just the mirror analogy, that does make sense. Assuming that there is a curve, but the jury is still very much out on that one.
So what was done was you measure some stars that you think are probably close to you, and then you look for that same constellation somewhere else. You look for more copies of it. Because if you could find a repeating pattern, you'd say, there's a pretty good chance I'm looking at the same stars, but from a different position.
That makes sense.
And we didn't find a curve, unfortunately. That would be fun. We didn't find one.
But I'm assuming we have
prove-
very limited like ability to see these patterns. Like we only can see so much of the universe with their current technological limitation.
You actually hinted at this earlier. You described the universe is expanding. And this leads to kind of an edge in the sense that there are things that might exist that you could never reach in a spaceship. Or even you'll never be able to see them.
Theoretically, yeah. Yeah.
No, very, very concretely.
Wait, but even if you were to make like a machine that went at like the speed of light?
Yes, because it turns out that our universe is expanding from everywhere, and there's a distance away from Earth where the amount of increase in space is bigger than light speed. So a light beam leaving from Earth will never actually get that far away from us. I'm probably explaining this poorly.
No, that makes sense because if the light beam is going and something is going faster, it's like you can almost think about like cars. If a car is ahead of another car and the car that's ahead is going faster, then the car behind will never catch up.
That probably gives you the right idea, although it's you just described something like a Galilean transform, and we learned that those don't work with things going light speed.
Yeah, I figured that there's probably some differences when you get to that. Like, it's like things get also very heavy, like because of the E equals MC squared equation or something.
Well, you get an effect called time dilation. That's for sure. you start time. If you're going very fast, you perceive time as passing more slowly for you than everyone else. It's not like a drug trip slow mo deal. It's just if you were watching a clock somewhere else, it would be ticking faster than a clock you were holding in your hand.
Okay.
But anyway, this idea. We call it the observable universe.
Okay.
There's a like a sphere around the Earth that we call the observable universe because anything outside that sphere we can't know about.
Yes. Yeah. True.
This is probably the first thing I talked about with Sheldon, actually, or with Don.
What was Don's thoughts? I'm curious.
He was curious about the expansion of space, which a lot of people seem to have heard about, but they don't have a great picture in their mind of how that could work.
I'm in the same boat.
A lot of people seem to think that the Big Bang was an explosion, and all the galaxies and stars are flying away from the explosion. But that's not the right way to think about it.
What is the correct way to think about it?
So it's easier if we talk about a 2D universe. And because we are talking about a curved one, let's make it a balloon. Imagine your whole universe exists on the surface of a balloon.
Okay.
The expansion of our universe is like the balloon inflating. So if you put a dot anywhere on the balloon, and you blow it up,
yep.
The dots get further apart.
Yes.
And it doesn't matter where you put your dots. Anywhere you choose, they'll always end up further apart.
Okay, this makes sense so far.
So our universe, and we know this for real, does a similar thing in 3 dimensions. Any 2 points are always being stretched apart.
Does that mean that theoretically, let's say our solar system or our galaxy and the next galaxy are slowly growing apart?
They would, except for they're also being pulled together
by gravity.
Right. So the reason that this stretching doesn't kill all of us is because the forces holding atoms together and holding molecules together are strong enough to when space gets bigger, they just pull back together.
Okay.
And gravity is also strong enough to do this for things the size of galaxies. There is I think it's called the local supercluster of galaxies, and the Milky Way is just one of them. The gravity between them is strong enough to overcome this stretching and keep them relatively in the same position with each other.
Got it.
But if you talk about a galaxy, go ahead.
I was just going to ask, is there a place where the gravity isn't strong enough?
Yeah, if you go far enough away, the gravity between a sufficiently distant galaxy is weak enough that the stretching will start to move them apart.
Got it.
And one way we can tell this is because if you look at basically anywhere in the night sky, on average, what you'll see is things moving away from us.
Wow. I mean, I knew the universe is expanding, but I would never think of star positions moving that far, theoretically.
Well, the way you tell is by this thing called Redshift, which maybe you've heard of before.
I have not actually. Why don't you explain what that is?
So the easiest way to explain it is probably, have you ever heard of an ambulance go past your house?
What was that? Angular or ambulance?
Ambulance.
Ambulance. Oh, so Doppler effect or something?
It's that. When a thing generating a wave is moving towards you, The waves all get stacked up closer together, and you experience it as an increase in frequency or a higher pitch noise.
Yes.
And when
Yeah.
the ambulance drives past, the waves are getting pulled apart, and the frequency is lower, and you hear it as a lower pitch noise.
Yeah. Yeah. So how do so that I've heard of before. What how does that apply? Is that like a similar phenomenon with how stars move?
So stars are giant objects that are constantly spewing out a wave, which is light. And if the star is moving away from you, then we're going to end up stretching out that light wave, which reduces its frequency. So if you know what frequency the star is really emitting, you can compare that to what frequency you're seeing, and you can say, how much is it stretched by?
Ah, that makes sense. What's the way to figure out its true frequency, though, or like a base point?
So I'm not sure about this, but I think what we do is we have a pretty good idea of the average life cycle of a star. And if you know what that is, and you know what the star is made of, which is, fairly also on this life cycle, you can say the color of the star should be this frequency. And we assume that the stars are kind of uniform everywhere in the universe. So we can say, I expect that star to be this certain color of yellow. And it turns out that it looks red to me. And red is what you get if you stretch out the light. It turns more red. And eventually it turns into like infrared or like a much lower frequency you can't even see.
Interesting. Okay. So using these averages, we can kind of tell how much, I guess, spread has happened for a given.
And the term is redshift. Because
okay.
It's the color. And we also get blue shift, if you're curious. Sometimes.
Yeah, what's blue shift? Same kind of deal or a different phenomenon?
Same thing, backwards. It's the part where the ambulance is driving towards you.
So if it's like the balloon metaphor, how would something like move towards us? The force of gravity.
It's less crazy. But you could imagine like maybe the star is in a binary system and it's orbiting in a circle, and so half the time it's moving really quickly away from you because it's in the away part of its orbit, and half the time it's moving pretty quickly back towards you to complete the circle.
Okay, so there's like a lot of different forces. There's gravity, there's universal expansion, there's orbiting. So like that could affect like the red and blue shift at a given time. Okay.
The expansion is interesting because if you look at enough things in any arbitrary direction, you'll see the same kind of like underlying red shifting. Which means there's got to be something really general and big going on.
Makes sense. And in this case, you're prescribing that to the universal expansion.
Yeah. The only other way you could be is if, and this is not what happens, somehow the Earth was the center of the universe, and literally every object was moving away from us. And that would be crazy.
I know the Catholic Church in the 1400s wanted that, but I'm pretty sure that's not right.
Right. Like it's we're gonna be Copernicus here and say maybe we're not the most important thing anywhere.
Fair enough. So I'm curious where black holes fit into this, because I've heard like interesting things happen within like black holes that could be related to this. So I'm curious where that fits in.
So remember we talked about the observable universe and how there is kind of this distance away from us where we can't observe anything that happens beyond that distance because we'll just never
we'll never get
so in that sense that boundary is called an event horizon because information about events can't cross that horizon.
Okay, that makes sense.
A black hole has, we think, but we're not sure, a similar feature where at some distance away from this very dense glob of mass, there is an event horizon where anything that happens inside never gets out.
Got it. And black holes form from suns imploding or something else?
Um, a black hole will form anytime enough mass is in a sufficiently small area. It's called there's an equation for it, and it's called the Schwarzschild radius. Schild? I speak a little bit of German, enough to pronounce that one word.
Okay.
It turns out that what word translates to black shield, but it has nothing to do with physics. That's just the guy's last name. He just had a
Okay.
very convenient last name.
Oh, nice. Pretty cool last name.
So if you get every amount of mass has a Schwarzschild radius, and if you can get all of the mass inside that radius, it will be a black hole.
Okay.
So for the sun, that radius is I think like 3 kilometers. Someone could look it up right here.
Yeah.
But imagine smushing all of the sun into a ball 3 kilometers across.
Okay. So much smaller than it is now. Yeah.
Yeah. For the Earth, I think it's like a centimeter or something.
Oh, wow.
So it's very hard. It's kind of hard to construct one of these. We're lucky though, because if you want to find a black hole, because as you keep dumping more and more mass together, that mass will collapse on itself under gravity. Like it won't have any way of keeping itself apart, and the radius grows faster than the size of the ball. So you just need to dump enough stuff together, and eventually this radius we're talking about will leave the outside of the ball.
Got it. And then you get the black hole. Cool.
Yeah. And you mentioned a star exploding. A similar that can also help you if you want to do this. It's kind of similar to how a hydrogen bomb actually works, or no, a nuclear bomb works. Basically, when a star explodes, it doesn't explode from the middle. It explodes from a shell around the middle.
Okay.
So imagine you have this fairly big core of a star, and then you set off an enormous explosion on every side simultaneously. For a little while, you're going to smush that core much smaller than it used to be. And when you do that, if you can smush it enough, you'll push it inside its Schwarzschild radius, and then it'll be stuck that way.
Okay. So basically, and is this more fission than fusion, or the other way?
Stars operate on fission.
Fission. Wait, I thought it was fusion.
Oh, sorry, you're right. No, stars operate on fusion.
Okay.
You 100% right on that. But yeah, it's the explosion at the end that does it. That pushes enough stuff close enough together that it is stuck in this new compact form.
Got it. And just quick question, how do stars even basically die off in the first place? Did they just run out of enough materials to keep it going, basically?
Yeah, so stars use this if you think of a star like a house, it's a house being held up by nuclear explosions.
Yeah.
Gravity is trying. Well, no, gravity doesn't try and do anything. Gravity just does things. But gravity is pulling all of the hydrogen that is a star into this ball.
Okay.
And when it gets the ball small enough, the hydrogen is really hot, and it starts to fuse. And that is an explosion that pushes the hydrogen outwards again. And it does this for a very long time until there's not enough hydrogen left. And then gravity pulls it smaller. I mean, it does it kind of in a smooth, continuous way. And then the helium that you got from fusing the hydrogen starts to happen. And there's this whole almost like a food chain of what new fusion starts to happen at different parts of the star as hydrogen runs out.
Okay.
And it stops with usually around iron. You can't fuse iron for profit. When you try it, it costs energy. So it's not a useful way of like heating up your star.
And eventually it runs out, and then you.
So the end is a little confusing. I'm not really sure about why that happens. Something happens that if the star was big enough, it'll explode. Or it could just like kind of quietly die out and not do anything interesting.
Got it. And if it was to die out in a way that like where everything would kind of collapse in this like radius, this necessary radius, then you could get a black hole.
Yes.
Okay. Cool.
It's also not the only way though. You can also, in theory, the matter inside your black hole doesn't need to be one big lump. So you could have, like a whole galaxy. If it was small enough, it could form a black hole where it's still full of stars and planets, but there's enough mass in a small enough space that there is an event horizon around.
Okay.
But from the perspective of inside, I assume everything's very strange, but you've still got separate objects. And you might not even notice, like if you were used to it, maybe you'd think this is just how things are.
Wow. So you can get basically any situation where any mass, regardless of even if it's like different objects, are within a small enough radius.
Yes, and that one's actually convenient. If you have a small black hole, getting too close to it is like going to rip you apart. It's gonna like straight up kill you. But as the event horizon gets bigger, as the radius gets larger, the amount of ripping goes down. So if you have a very, very large black hole, you might be able to like toss something into it, and it wouldn't be torn apart by doing that.
What would happen to that object?
It would just be inside. It's stuck there. It has no way out. There's literally no path that it could take. Any direction it tried to move would bring it closer to the center.
Interesting.
But it is still like a single object that you could talk about like a baseball or a person or something. It's not like totally ruined.
Interesting. So theoretically, humans could survive black holes.
If you can find
a big enough
just a
one,
freakishly enormous one.
Okay. So there's hope. There's hope yet for the crazy space explorers out there.
I don't think it's going to be fun. I certainly don't want to be on that spaceship.
Elon Musk is already, getting the voyage ready.
Oh yeah, I'm sure he's got a Falcon 1 built. He's got some crazy people lining up to be launched at it.
So, how do black holes inform us of like universal expansion, or like some of the topics that we've talked about thus far? Is there any like links that we can draw between them and the other stuff?
Well, they are useful in one way I can think of, which is knowing how fast information moves in your universe. So maybe you've heard of this thing called a gravitational wave.
Yes, but it's been a while. Like I've heard that term, but it's been a while.
So it's analogous to a wave of light. And usually physicists use light as like a stand-in for how fast can information go.
Yep.
Because that is like the maximum speed, right? But you would have a problem if gravity was instant. So, like, it must be the case that a black hole somewhere very far away, when it moves, you don't know it's moved until much later.
Okay, because of the delayed effect of gravity.
Right. There has to be like a delay, propagation delay between the gravity bending at that hole and you feeling the pull.
Okay.
So if there's a delay, then you can build a setup that will give you an oscillation in your like perceived gravitational force.
Okay.
And one way you can do that is by having a pair of really heavy things, either stars or black holes or something, orbiting each other. Because when they do that, you will get one of those objects will move close to you and then far away, close to you and then far away. And this will create like an up and down from your perspective of how strong is gravity in that direction.
Okay, so yeah, it's a way to measure it, like you said.
So it gives you this wave effect, and it's very nice to know that like yes, gravity is a speed limit. Because otherwise we'd have some problems.
That makes sense.
It's also useful because this one is weird. Have you ever played Kerbal Space Program?
I don't think so.
Okay. So if you are in orbit around something, maybe a planet, what way do you need to fire your rocket if you want to go down to the planet's surface?
Towards the planet, or like from the space side, from the out of the atmosphere side into the atmosphere.
A lot of movies would have you think that, but that is not the way to go. It turns out that you, as a spaceship in orbit, it's more like you're falling in a circle.
Okay. I'm trying to conceptualize this, but yeah, okay. Continue.
So what you need to do is slow down. You're going too fast. You're constantly missing the planet you want to hit. The trick is you need to like put the brakes on so that you're just standing still, and then the planet will happily have you fall towards it.
So let the gravity kind of take care of itself.
So you have to fire your rockets against your direction of travel. You have to like point them out your windshield and turn them on to like steal the speed you have. And as you do that, you'll just move closer to the planet.
Wait, would you not just let gravity take over, or are you actively propelling against the planet's atmosphere?
It's both. Like you slow down so that gravity can pull you in. Because gravity won't slow you down. You need to do that yourself.
Yeah, that makes sense.
This same kind of thing is a problem for how do black holes merge. Like, imagine you have two black holes, and they have a lot of gravity, so they're pulling each other towards each other, but they're not quite on a straight line collision course. They miss by a little bit. And now they're going to be stuck orbiting their common center. They're going to there's going to be some point halfway between them if they're the same size. And they're going to end up stuck spinning around that point. And they have no way of slowing down. If they want to hit each other, like our spaceship orbiting our planet, they don't need to push in. They need to slow down. And
makes sense.
In space.
Yeah. Oh no, go for it. I was processing things, but this is starting to make sense when I think about it. Yeah.
So we think one of the ways they can do that is these waves. I'm a little hazy on this part, but like when I say slow down, what I mean is uh, dump your kinetic energy somewhere. Dump your energy of movement somewhere else. In space, that's really tough because there's just nothing else around to give it to. But I think what you can do is you can put energy in these waves and it will move away from your orbiting black holes. And little by little, as they shed more and more energy, they'll eventually move close enough together to hit each other.
Got it. This part is the black hole part is a little bit trickier for me to wrap my head around, but I think the concept makes sense from how you describe landing a spaceship on a planet.
They're a little, yeah. The reason we use black holes is because they're the only things that are usually big enough for us to even measure the waves.
Hmm.
But it could be anything. Like the same problem happens with any two things stuck in an orbit.
Yeah, makes sense. Let gravity do its thing.
It's a problem that most people, for good reason, never think of. Like they're so we as humans are so used to living in this big soup of air
Yeah.
that like the rules for how things move almost everywhere else feel wrong to us.
Yeah, I mean, I feel like we don't really think about space that much outside of our school, unless of course you do more schooling in that topic. So like it's hard for us to conceptualize because we don't really think about these problems, but they are fascinating. Like I think the stars and the sun, they're a big part of our lives, and sorry, this is getting very high level, but also like with space travel potentially in the future and potential mission to Mars. Like these are things that are like big, but like I don't think like we kind of emphasize kind of outside of high school.
Uh, yeah, and even if we do it there, I mean, I don't know about you, but I was not maybe the most studious person in high school.
Yeah, yeah. I mean, we can't expect 15-year-olds to have the most enthusiasm um, about space. Some of them definitely do, but definitely not all.
It's a good thing some of them do. Otherwise, no one would be building rockets.
Yeah. Yes. Yes. Um, yeah. I mean, I think we still have some time, but I was wondering if there was like any particular topics that you wanted to talk about or dive into, or thought experiments you wanted to do that we hadn't got to cover yet.
Um, well, did we decide on a shape? What shape do you think the universe is? What's
All right,
your
let's go back to this. I'm still gonna stick to my guns, and I not that I can back this up and say that since it's ever expanding, it's hard to come up with a finite shape. But I might steal your curve idea because I think it's the best one I've heard so far. Not that I've thought about this question that much in depth.
fair enough? So your vote is for infinite and flat, or infinite and curved.
Yeah, probably more of the latter. I guess maybe flat just has too many overtones to like flat Earth, but yeah.
Okay, well, I've learned one thing about you, Alex.
Oh man, did I choose the wrong answer?
It's not my favorite answer, but it's not a totally wrong answer either.
Okay,
So
what was Don's answer?
I think he refused to answer.
Ah, come on, that's lame.
I
And your answer is
Yes,
just the curved shape, right?
yes, I think it curves back on itself.
Okay, cool.
Um, and I guess if there's one other thing that is interesting, or at least that is close to my heart, it's
Hmm.
that don't put your hopes on Mars.
In terms of what hopes on Mars?
Living there.
Oh, I mean, my intention was never to live on Mars, but I do know that Elon Musk is pretty big about on this.
Uh, the Earth is the only place. The Earth is like we're made for it. It's so perfect for us. There's no if anything we should be making it better. Don't try and run away somewhere. The Earth is already by far the best place anywhere because we grew up to fit perfectly with it.
You heard that, everyone, ladies and gentlemen. Earth is better than Mars. You got that straight from the Single Dads podcast.
Okay.
No, but I do think, yeah, this idea of Mars terraforming, solving, all the problems like overpopulation is probably a little bit overstated. I definitely agree with that sentiment.
I leave my Mars terraforming to board games.
That is fun. Yeah, I mean, that's a much more fun way to do it, I would say.
Takes 3 hours, not thousands of years.
3 hours, not 3,000 years, yeah. But yeah, Nick, honestly, this was the most I've ever had to think about space, and probably the most I've intellectually been challenged on this podcast. But I love it because it's making me think about these things in new ways. And now I'm like, I kind of want to look up like red and blue shifting and some of these ideas more in depth, like gravitational waves, because like it's been a while since I've explored these ideas. So I very much appreciate you kind of awakening that curiosity, and I hope all the science folks out there are also loving it too.
Thank you for having me, and I hope I didn't gravely offend too many of your listeners with misinformation.
No, I think everything you said made a lot of sense. Before I leave, were there any resources you think would be useful to people who wanted to learn more, like things that you use to learn more about these topics?
I don't have any recommendations. I have a Google News feed full of articles that I cannot escape from that just keep telling me more about it.
Nice. Well, if you do think of something, just let me know and we can put that links in the description. But once again, thank you so much, Nick, and thank you to everyone listening, and thank you to Don for putting this together. I really appreciate all of you, and hope you have a good rest of your night, Nick.
You too. Take care.